Hello friends, welcome to another lecture on mathematical physics special function. And in this video I'm going to prove this relation. Okay, I'm going to solve this question. It is very important for BSc students, mathematical physics, okay, where Pn of x is Legendre polynomial. And I would like to suggest, please watch all the videos from from the starting of the playlist of special function. I have given the link in the description box. And before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you get the hype option to hype the video, please do hype the video. Okay, and this is my Insta ID, OJHALAKHYAJIT123. Please do follow me on Insta. Okay, so now let's start. So here we need to prove this relation. Okay, so how to prove this? Let me write proof here. First, hope you have the idea of generating function for Legendre polynomial. So if you don't know, and if you don't know about the generating function of Legendre polynomial, please watch the previous lectures, at least based on those watch those lectures based on the Legendre polynomial. Okay, and this series of special function will be continued. Okay, in this series I will complete the syllabus for CSIR net, the special function portion only. I am talking about special function. Okay, so for other chapters playlist will be different. Okay, and in this playlist I will include solution of previous year's questions of CSIR net examination. Okay, so please stay connected, right? So now let me write the generating function. We know that 1 minus 2x into z plus z square whole to the power minus half is equal to summation zn pn of x. So here that means this function is generating function because this Pn of x is the coefficient of z to the power n in the expansion of this. So that's why this is generating function of Legendre polynomial. Pn of x is. Now if we square this both sides, then what we're going to have on the left hand side, we're going to have 1 minus twice x z plus z square whole to the power minus 1 on the right hand side. Now you see, if you square this, then you simply can't write only this z to the power twice n pn of x square. You just can't write this. Okay, it will include one more term, that is 2 summation m plus n pm of x into Pn of x. We can write this. Okay, now you see, let me explain why this term should be written. So here summation is from n is equal to 0 to infinity, right? From n equal to 0 to infinity. For simplicity, let me consider just only two terms. Only three terms from n equal to 0 to 2. Suppose let me take only two terms, 0 to 1. If you consider that summation, then it will be just give me a second. Let me consider this term. Here you see, let me consider this term first. So here for n is equal to 0 to infinity, if we take it for n is equal to 0 to 1 only, then its expansion will be of this form: z to the power 0 p0 of x plus z to the power 1 p1 of x right? Now if we square this, then what we're gonna have? We're gonna have 2 into 2 z to the power 2 into 0. That means 0, but let me write this way, then it will be easier to explain. Z to the power 2 into 0, okay, p0 of x square, then plus 2 into z to the power 0 p0 of x into z to the power 1 p1 of x plus z to the power 2 into 1, you can write that way, p2 of x, not p2, p1 of x square. Okay, that's what we will get. Actually here we are getting z square, applying a plus b whole square formula. Here we are getting z square, but instead of writing z square, I have written z to the power 2 into 1. Okay, so to observe the pattern, actually now from these two terms, including these two terms, we can write using summation, that summation from n is equal to 0 to n is equal to 1 z to the power twice n. If you put n is equal to 1 and 2, then you will as 0 and 1, then you will get these two terms, and here we're gonna have pn of x square. Okay, sum of these two can be represented by this part, and plus then 2 into z to the power 0, z to the power 1, that z to the power 0 plus 1, then p0 of x, then into p1 of x. Now you see the observe the pattern properly. So here you see this part is nothing but this one, and this part is nothing but this one. Here only we have taken from 0 to 1. Okay, if you take it from 0 to infinity, so you can compare with this part. Okay, hope you have understood this. We're gonna get more such terms, but here only we are taking two terms, right? If you take 3 n is equal to 0 to 3 n is equal to 0 to 5, you're gonna have many terms of this form, so and all those can be written using summation in this form, right? Hope you have understood this. Okay, and it will be better if you remember this result. Okay, I tried to explain you how we have got this. Okay, but I don't know you have understood or not. Please let me know in the comment box. Okay, I will come up with a better explanation in another video. Okay, so it will be better if you remember this result. Okay, because in examination you can't get enough time for this kind of analysis. Okay, so that's why now let me clean this part. We don't need these things, just I have written all these things to explain this form that we have got. Okay, result form of this result. Okay, so now you see, now let us integrate it with respect to x, integrating both sides with respect to x. Then what we're gonna have, so on the left hand side, integration from minus infinity to plus infinity, 1 minus twice x z plus z square whole to the power minus 1 dx. We are integrating with respect to x. So equal sign, on the other hand, on the other side, summation from n is equal to 0 to infinity. I'm not gonna repeat all the time this n equal to, I'm not gonna write this n is equal to 0 to infinity all the time. Okay, hope you will understand that if I write summation only. Okay, z to the power twice n. Here we're gonna consider we're going to treat this as a constant because we are integrating with respect to x only. So my integration from minus 1 to plus 1, pn square of pn of x square dx, right, plus integration here to summation z to the power m plus n, z to the power m plus n, integration from minus infinity to plus infinity, Pm of x into Pn of x dx. That's what we're gonna have. Now you see, in the last video we have discussed about orthogonality of polynomial function. Link is in the description box. Please do watch that video. So according to that property, this result is equal to nothing but 0, right? Hope you know these things. So if this, then we can write that let me write this part on the left hand side first. Okay, summation z to the power twice n integration from -1 to +1 -1 to +1 Pn of x whole square dx. On the other side, this is nothing but integration from -1 to +1, right? 1 by 1 minus xz plus z square dx. That's what we're gonna have. So now you see, here what we're gonna have, that now you know integration of this form. Suppose you have integration 1 by, suppose you have a plus x, or if you have suppose a plus bx dx. So if you integrate it, then what you're gonna have, you're gonna have log of x, log of a plus bx, b of x, and 1 by ddx of this a plus bx, right? Hope you know this thing. Okay, or you just you divide it by the coefficient of x, that is here b. So similarly you see, if you compare this one with this part, here we're going to treat the z as constant as we are integrating with respect to x. So here we're going to treat this part +1 as a here in this case, and we're gonna treat 2z as b. Okay, here minus b. Okay, if you compare with this result. Okay, so then you see, then what we're gonna have in this case, so we're gonna get log of this 1 minus twice xz plus z square, and here we're gonna have 2. So here you see the coefficient of x, the coefficient of variable is here -2 into z, right? -2 into z. This is this term can be written as -2z into x. So here this part is the coefficient, right? So here we're gonna write that, just give me a second. Okay, we're gonna write this -1 by 2z, right? Hope you have understood this. So now let me clean this. Okay, that's what we have got. So now let me take a new slide, and let me go to a new slide. Let me copy the last step. Okay, so here is the last step we have got, and this is the integral result of the integration. Let me write here. Okay, so this is what we have got after integrating, but let me write the upper and lower limits. Okay, that is -1 to +1. So here I forgot to write that, I think. Okay, so I have cut it here, so just I have written here. Okay, -1 to +1. So now you see, if you put if you replace the x by 1, then what you're gonna have? If you replace the x by 1, then you're gonna have log 1 minus twice z plus z square, then lower limit minus log of, if you replace the x by -1, then you're gonna have 1 plus twice z plus z square, right? So first put the upper limit, then put the lower limit, and results should be subtracted like this, and this is what we have got. Now we know that log m minus log n, this property is known to you, I think. Log m divided by n if you don't know, write this property. So we're going to use this property. According to that property, what we're going to have, 1 by 2z, here we're going to have log of 1 minus twice z plus z square divided by 1 plus 2i z plus z square. That's what we're going to have, right? Hope you have understood this. So now you see, just let me write it properly. So this is nothing but a minus b whole square. This is a plus b whole square, right? Here it is 1 square minus 2 into 1 into z plus z square. That means 1 minus z whole square, right? So here it can be written this way: 1 by z minus 1 by z log of, here we're going to have 1 minus z whole square in the denominator, 1 plus z whole square. So here as a whole we're going to write square here. And we know the property of log of m to the power n can be written as n into log of m. So if we use that property, we can write this 2 here, and if we write this 2 here, this 2 will be cancelled by this one, right? So at the end we end up getting this if you make it positive, then you have to change this numerator to you have to change the numerator and interchange the numerator and denominator. Then you can write 1 by z positive. If you write it positive, then it will be log of 1 plus z by 1 minus z. Remember this: if you have log m by log n, if you have minus here, if you make it positive, then this n goes up and this m comes down. Okay, that means minus log m by n can be written as plus of log n by m, right? Hope you have understood this. Okay, now again we can write this in this way, that half of, in order to expand this series of log of 1 plus z minus log of 1 minus z, as I have already told you that we can write log of m minus log of n is equal to log of m by n, right? So now this one, here you see this one in this form, so I am writing in this form, right? Hope you have understood this. Okay, so now let me copy the last part and let me go to a new slide. So here is a new slide, and let me write the final result we have got. This is the final expression. So let me copy this and go to the new slide. Okay, so now you see, you must remember these two series, important series. Okay, those are 1 by z, log of 1 plus z, log of 1 plus z is equal to this series z minus z square by 2 plus, alternatively positive negative, z cube by 3 minus z to the power 4 by 4 plus dot 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 dot. Okay, these are very important series. So if you are a student of physics, mathematics, if you want to study, if you want to understand and mathematical physics, then you must remember some special series like logarithmic series and exponential series, those kind of special series. Okay, sine function in the form of series, you must remember those kind of series. Okay, because those are actually frequently used in mathematical physics, right? Hope you got my point, what I'm trying to say, that minus an expansion of this series 1 minus z will be of this form: minus z square by 2 minus z cube by 3, then minus z to the power 4 by 4, then minus dot 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 minus z to the power twice n plus 1 by twice n plus 1 minus dot dot dot, so on. These are infinite series. Here you see, in this case, if we open this bracket, then what we're gonna have, then we end up getting this, let me write here, 1 by z. First let me copy the first part of this bracket. So here is the first part, and if you open this bracket, then this sign will be changed. All this sign inside the bracket will be changed. Negative sign will be positive. Okay, then you will get positive z square by 2, positive z cube by 3, positive z to the power 4 by 4, positive dot 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 so on, right? So here negative positive terms will be cancelled. Here this one will be cancelled by this one will be cancelled by this one. Alternatively, one after one terms will be cancelled. Okay, what will be the remaining terms? So remaining terms we will get 2z. Okay, so z plus z, 2z cube by 3, and 2z to the power 5 by 5, and so on. Okay, that's why we're gonna have 2z plus 2z cube by 3 plus 2z to the power 5 by 5 plus dot 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 2 into z to the power twice n plus 1 by twice n plus 1. Okay, that's what we're gonna have. So now you see what we can do here. If we multiply 1 by z with all these terms, then here this z will cancel this one. Similarly, this z cube will be z square. Similarly, z to the power 5 will be z to the power 4, and so on, right? So then we're gonna have 2 plus we can take the 2 common, right? 2 is taken common. Then here we're gonna have z cancel 1. Here we're gonna have z square by 3. Then next time we're gonna have z to the power 4 by 5 plus dot dot dot. Here 2 is taken common, and if we cancel this one by z, then we're gonna have z to the power 2n. That power will be reduced by 1. Okay, as we have cancelled it by z, right? Hope you have got my point, what I'm talking about. Okay, dot 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 so on. That's what we have got. So now let me copy this and let me take a new slide again. So here is the final result. Let me write this one here. So this is the final result, right? Let me write it properly. Okay, now let me copy this and let me go to a new slide. Here is the last step. Okay, now you see what we're going to do here. This part you can see. So here this 2z square can be written as z to the power. Okay, just let me write one more step that will make the things more clear. So here 1 can be written as z to the power 2 into 0 plus z square can be written as 2 into 1, z to the power 2 into 1 by 3. So instead of 3 we can write 2 into 2 plus 1, not 2 into 2 plus 1, sorry, 2 into 1 plus 1, and here 2 into 0 plus 1, right? And in the next term we can write z to the power 2 into 2 divided by 2 into 2 plus 1 plus dot 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 z to the power twice n by twice n plus 1 dot 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 so on. So we can write this in the form of summation, using summation, that from n is equal to 0 to infinity z to the power twice n by twice n plus 1, right? We can write these things. Hope you have understood this. Okay, if you keep putting z equal to n equal to 0, 1, 2, 3 dot 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 so on. As I have already told you, here though I have not written, here also we have n is equal to 0, then to infinity, this, right? We have this. So now you can see that here, if we compare the coefficient of z to the power n on both sides, comparing the coefficients, of z to the power not n twice n, okay, twice n on both sides. And from here you see, so this 2 can be written here, right? And from here we can we can write this way, we can write the term this way, right? So here you see this part is coefficient of z to the power twice n, here this part is the coefficient of z to the power twice n, okay. So comparing this coefficients of z to the power twice n on both sides, we're gonna have integration from -1 to +1 Pn of x whole square, Pn of x whole square dx is equal to 2 divided by twice n plus 1. That's what we will get. Hope you have understood this. So this is what we needed to prove. So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.